So what if I told you that a single line of code, one that was supposed to make things cleaner, could actually bring your entire system to its knees? Yeah, today we're diving into a real engineering mystery, a case where a totally harmless-looking refactor caused an absolute performance meltdown.
Just imagine this for a second. Your most critical API, the one that's usually lightning fast, responding in a snappy 15 milliseconds, suddenly it just skyrockets to 180. We're talking a 10-time spike in latency. And this wasn't some slow, creeping problem. Nope, this was a sudden, catastrophic failure that had the entire engineering team scrambling, just trying to figure out what was going on.
And here's the part that just makes it so maddening. The change wasn't some big, complicated new feature. Nope. It was a routine refactor, a simple cleanup meant to make the code better. But as the team was about to find out, its impact was, well, anything but harmless.
Okay, so let's set the scene. We're talking about a supercritical session management API for a major SaaS platform. This is the thing that handles logins, user preferences, you get the idea. After this one deployment, not only did the latency go through the roof, but CPU usage literally doubled, and the whole service just started to crumble under the load.
So, what's the first step in any crisis like this? You stop the bleeding, right? The team rolled back the deployment, and, like magic, performance just snapped right back to normal. But to be absolutely sure, they redeployed the change, and boom, the problem was back, instantly. There was zero doubt now. The culprit was hiding somewhere in that last deployment.
All right, now the real hunt began. It wasn't the database, wasn't the network. The team eventually traced it to a single, deceptively simple change in the session cleanup logic. And get this, it was a change that had sailed right through code review without raising a single red flag.
And here it is, the culprit, a single operator change. All the team did was replace setting a property to null with the delete operator. Now, why would they do that? Well, it just felt cleaner, right? Deleting the property removes it entirely, leaving a tidier-looking object. From a functional standpoint, the outcome was exactly the same. But from a performance perspective, it was an absolute catastrophe.
This brings us right to the heart of our mystery. I mean, how on earth can just swapping null for delete cause a system-wide meltdown? The answer, it turns out, lies deep inside the JavaScript engine that powers Node.js, the V8 engine.
So, to solve this, we kind of need to put on our V8 detective hats. See, V8 is incredibly fast because of this powerful, almost hidden optimization called hidden classes. This whole system is what enables something known as the fast path. So what in the world is a hidden class? The best way to think about it is like a secret blueprint that V8 creates for every single object. This blueprint describes the object's shape, basically what properties it has, and crucially where they're located in memory. When V8 knows the shape, it can access those properties ridiculously fast. And V8 builds these blueprints on the fly. You start with an empty object, right? That gets a base hidden class, let's call it C0. Then, when you add a property, say object.a, it transitions to a new class, C1. You add another property, object.b, and it transitions again to C2. V8 is built to expect this kind of predictable, stable chain of events. It loves it.
Now here's the real payoff. When you have thousands or even millions of objects that are all created with the exact same shape, they all share the same hidden class. This is the magic moment. It allows V8's compiler, TurboFan, to generate hyper-optimized machine code. It can access properties at fixed memory locations, almost like they were static C++ objects. This is the fast path we were talking about. Okay, so now we get to the villain of our story. The delete operator. It comes along and just completely shatters this beautifully optimized world we've built. It forces V8 to throw away all its blueprints and abandon the fast path entirely. So when you use delete, you're not just removing a value, you are fundamentally changing the object's shape. You're literally punching a hole in that stable structure we just talked about. And that act invalidates the blueprint, totally breaking the hidden class system for that object.
And this slide just illustrates the consequence perfectly. The object gets kicked out of fast mode and is downgraded to what's called dictionary mode. So instead of that fast blueprint-based memory layout, its properties are now just stored in a generic, slow hash table. Accessing a property is no longer a simple direct memory read, it's now a slow, painful dictionary lookup every single time.
And the performance penalty here it's just staggering.
Accessing a property on an object that's been forced into this dictionary mode can be up to 100 times slower than on an object that got to stay on the fast path. 100 times.
But wait, it actually gets worse. This slowdown is contagious. When a function that was previously highly optimized for those fast objects suddenly encounters one of these new, slow dictionary mode objects, V8 basically panics. It deoptimizes the entire function, falling back to a much, much slower execution mode. So this poison, it spreads from that one single changed object across the entire application.
So, okay, how do you climb back from this performance cliff? I mean, understanding the problem is one thing, but the solution requires making a really smart trade-off between memory and speed.
And this table here lays it all out perfectly. Using delete, sure, it has the lowest memory footprint, but the performance cost is catastrophic. It's just not worth it. The clear winner, by a mile, is just setting the property to null. Yeah, it uses a tiny bit more memory, but by preserving the object shape, the performance impact is pretty much negligible.
So, armed with this new knowledge, the team's fix was incredibly simple. They just went back through the code and replaced every single instance of that delete operator in that critical hot path with a simple assignment to null.
And the result? It was immediate and it was dramatic. Latency plummeted from that painful 180 milliseconds right back down to the happy baseline of 15. The CPU usage went back to normal. The crisis was over. The mystery was solved.
But, the story doesn't really end there. The real takeaway is a super crucial lesson for pretty much every engineer out there. Understanding how your runtime actually works isn't some niche micro-optimization. It's fundamental to building robust, high-performance systems.
So let's just distill this whole thing down into a few key principles you can take with you. First, in any performance-critical code or hot paths, try to treat your object shapes as immutable. Second, prefer setting properties to null or even undefined over ever using delete. And third, and this is a big one, always remember, the code that looks the cleanest isn't always the code that runs the best. You have to understand your runtime's optimization model.
And let's be really clear here. This isn't just some abstract theory. This single operator, chosen purely for aesthetic reasons, cost a real company days of frantic investigation. It degraded their customer experience and put their entire service at risk of a major outage, all from a supposedly harmless refactor.
And that leaves us with one final provocative thought to take with you. What other seemingly harmless, clean code is lurking in your project right now, just waiting to become the next performance bomb?